Okay, so just briefly some vocabulary terms you need to be familiar with. Saturated solution versus unsaturated versus supersaturated. So a saturated solution is a solution that contains as much solute as it possibly can at any given temperature or pressure. Okay, so there comes a point where a solvent can't hold any more solute because the amount of solute overwhelms the amount of solvent. Okay, so at the point where you've reached your maximum, that is saturated. Okay, unsaturated solution means that you have not yet reached that maximum amount of solute that can be held within your solution. Okay, and then supersaturated means that the solution actually contains more than a saturated solution. And so what you do in order to make that happen is actually to heat the solution up a lot in order to make the solute dissolve, and then you cool it down very slowly so that the solute will still stay in solution. Okay. Okay, so we'll go through this next part a little bit more slowly because we start getting a little bit complicated here as we mix concepts with equations. Okay, so there are three factors that affect the solubility of the substance, and this is sort of getting more specific than just the rule like dissolves like. So the first thing is very closely related to like dissolves like, and that is the structure effects of your substances. So in other words, if their structures are similar, then they're probably going to dissolve easily in one another. If they're not very structurally similar, then they're probably not going to dissolve very well in one another. And this is related to the idea that, remember, polar molecules are asymmetrical. Okay, and then nonpolar are symmetrical. So what that means is essentially the same thing we said before. Nonpolar things dissolve in one another, polar things dissolve in one another. And so we can relate that to their structure very easily. Okay, the next thing is the effect that pressure has on solubility. So solubility actually of solids and liquids is not affected very much by pressure, which should make sense to you because the same way their volumes aren't very compressible, they're not going to dissolve more easily in something just because pressure is being exerted on them. Okay. However, gases are very affected by the pressure, and they're directly related. So in other words, the higher your pressure, the more your gas is going to dissolve. Okay. And this is related to the equation known as Henry's law. And this C variable is the solubility of the gas. Okay, solubility of the gas in moles divided by liters. Okay, and then this value K is a constant, and that varies with what the substance is and what the temperature is. And then P is the partial pressure of the gas in atmospheres. Okay. So as the pressure increases, the solubility will increase. Okay, so they're on opposite sides of the equation, so it should be directly related. Okay, and so this image at the bottom just shows that as you're exerting more pressure on this gas, more of the gas particles are going to be forced into solution. Okay, so here's a particular example. So what this example does is it goes through the pressure differences of a soda bottle before and after it's opened. So take a moment and read over the question and then go through this work that's at the bottom. Okay, so this part right here uses Henry's law as it applies to before the bottle is opened. Oops, don't need two P's. Okay, So we have a constant that we're given, and then we're simply multiplying the pressure before the bottle is opened, and that tells us the concentration of our carbon dioxide, okay, before the bottle is opened. Then we do the same thing for after the bottle is open. Okay, we find the concentration of the carbon dioxide, okay? And as we would expect, it's substantially lower. Okay, and what's interesting about this is that we can set up an equality like this, where the concentration and pressure are related directly, but it's essentially like an initial and final setup. And you can set it up this way because the constant doesn't change. Okay, so you could solve for a variable there if you needed to. Okay. So in this next example, you have a certain mass and volume of a gas, and you can use that to find the initial concentration. It's fine that it's not in moles per liter. And then you're also told the initial pressure that's associated with that. And the question is, when the pressure changes, but the temperature stays the same, what is the new concentration? And so you can use this equation above, and you're again left with concentration in grams per liter, which is fine in this case because you have no way of finding moles without knowing the identity of the gas. Okay, and then the final thing is the temperature effect on solubility. And for a solid, the temperature might increase or decrease the solubility. It has to be experimentally determined. However, the solubility of a gas is always decreased as you increase the temperature. Okay, so make sure you understand that. It's not a direct relationship. Okay, so as we increase the temperature, think about what happens when you leave a soda can that's opened out on a hot day. The soda goes flat much faster, and that's because the temperature is higher, and so essentially more of that gas is going to be able to leave the liquid, and so it's not going to be as soluble because again the particles have more kinetic energy, and so they're going to overcome those intermolecular forces that are keeping them in the liquid. Okay, so that obviously relates to what we were doing last chapter as well. So similarly, in Chapter 10, we talked about what vapor pressure is, and it's just the pressure that a gas is exerting over a liquid. And we can think about the vapor pressure of solutions just as we had been thinking about them for pure liquids. Okay, so adding a solute, a non-volatile solute, so non-volatile just means that it doesn't want to escape very easily. It likes being dissolved. So adding a solute to a solvent lowers the solvent's vapor pressure. Okay, and so what that means is if we compare a solvent, so this has gas particles that are becoming liquid, and then liquid that are becoming gas, so it's that condensation, evaporation that are at equilibrium. So while that's happening for a solvent, the same thing can happen for a solution that has a non-volatile solute in it, but the difference here is that you have these solute particles that are taking up some of the surface, and so it's going to make it much harder for these solvent particles to escape into becoming a gas. Okay, so you can think of those solute particles as essentially barricading the solvent particles. It makes them more difficult to become a gas, and so therefore your vapor pressure is going to be lower because you have less gas when you've added a solute. Okay, so when we're thinking about how to represent this quantitatively, we use what's called Raoult's law, and you want to make sure that you're keeping track of what is solvent versus what is solution. Okay, so what this law says is that the vapor pressure of your solution is equal to the mole fraction of the solvent. Remember, chi is mole fraction, So the mole fraction of the solvent times the vapor pressure of the pure solvent. And this is usually something that will be given to you if it's not something that you are directly solving for. Okay, and then the mole fraction you would obviously find by looking at the moles of solvent divided by the moles of solution. Okay, so you multiply that by the vapor pressure given, and that tells you the vapor pressure of the solution. So this should make sense to you because this says that as the mole fraction of the solvent increases, in other words, as you have more solvent relative to solute, your vapor pressure should increase. Similarly, if you have more solute, this mole fraction value is going to become smaller and smaller, in turn making this vapor pressure also smaller. Okay, so that corresponds with the conceptual stuff that we just talked about. Okay, so let's look at this problem up here for a moment. So a solution is prepared by mixing 50 grams of glucose with 60 grams of water. So it should be clear to you that this is your solute, and then this is your solvent. Okay, and the question is, what is the vapor pressure of this solution at 25 degrees Celsius? Okay, and it tells you that the vapor pressure of the pure water, your pure solvent, is 23.8 torr. So go ahead and pause the screencast and take a moment to solve that problem. So what you probably want to do initially is convert each of the masses that you're given for your solvent and solute into moles. So you should find that you have 0.278 moles of your solute, the C6H12O6, and then you have 33.3 moles of water. So at that point, what you can do is solve for the mole fraction of your solvent. Okay, so you would put 33.3 moles, which is your moles of water, and then you put the total moles on the bottom by just adding both molar values together. Oops. Okay, and so when you do that, you should find that chi of H2O equals 0.992. Okay, and so then you can find the pressure of your solution by just multiplying that mole fraction by the constant that you're given initially. And what's nice is there's no unit on the mole fraction, and so your pressure unit right here corresponds to the pressure of your solution. And so when you do that multiplication, you should find that the pressure of the solution is 23.6 torr. Okay, and one thing, please make sure that this mole fraction is for your solvent. One of the biggest mistakes, and I have made it before too, is to do the mole fraction of the solute. Okay, so it's the mole fraction of the solvent that you want. Okay. Okay, so we can save this next in-class problem to do in class, but I wanted to at least go through this equation that is on this page. So we talked about Raoult's law as applying to solutions that have a non-volatile solute. And so if we have solutions where both of the components are volatile, you need to use this modified equation. So the P total represents the total vapor pressure of the solution. Okay, and then the chi's represent the mole fractions of A and B, respectively, and then the P naughts represent the vapor pressure of pure A and pure B, whatever those substances happen to be. And this derives from, the partial pressure equation, and so basically we're substituting in the Raoult's law for the partial pressures of each of our substances. So we'll go over, sorry, I just made a mess. We'll go over that next in-class problem in class.